Welcome to the Henstitute. So here I have the picture of myself getting ready to throw this ball. And so one of the things we talked about in the video that you just saw is that I am applying a force on this ball. So there is some kind of force acting, and this ball is going to undergo some kind of displacement. So we know that our work is equal to force times displacement times the cosine of theta, where theta is the angle between them. I'm going to look at a situation where the force and the displacement are in the same direction. So this is just going to end up being 1 because we're going to actually have the angle between them be 0 degrees. So theta is 0 degrees. So therefore the cosine of 0 is just 1. And what I'm going to show is how this kind of turns into a brand new concept. So if I go back to chapter 4, we know that force is equal to mass times acceleration. That's just Newton's second law, F equals ma. And then I'm going to drop down my d here. And so I always joke about this, that work makes you mad, because if I replace force with m times a, you do get mad for this. And then the next part is I'm going to keep my mass. This would be the mass of the object. But now what I'm going to do is with my acceleration is I'm going to go back to chapter 2, how I actually find the acceleration of an object. And this is the change in velocity. So Vf minus Vi divided by my time, and then keep my d on there. Now this made the equation look a little bit uglier, but we're doing okay with everything and nothing too crazy that we could actually have. Now I could leave it like this, but now I've got distance and time, and I don't really want to kind of deal with that. And so the last thing I'm going to do is take my distance and my time and realize that's average velocity. So if this is my average velocity, then I'm also going to take an idea from chapter 2 and how do I go about actually finding that average velocity. And we do that by taking the initial velocity plus the final velocity divided by 2. So that's what this whole concept is going to be. And then I'm multiplying it by just this Vf minus Vi, but I'm going to write that right there. And then I also have a mass kind of stuck on here. So it looks very ugly. One of the things I noticed is I could write Vi plus Vf here, but I can also write it the other way around. So if I grab my little eraser, I can actually change this from Vi plus Vf, since the additive property is summative, meaning you could flip it around whatever direction you want, then I should be able to take my final velocity plus my initial velocity. Now the reason I wrote it like that is now we have Vf minus Vi times the quantity Vf plus Vi. If I multiply those together, I know I'm going to get a difference of 2 squares. So what I eventually end up with is I'm going to bring this 1/2 out front. So I'm going to write it as 1/2 in front. I'm going to then write my mass here. And then for this, I end up with Vf squared, because there's the Vf times Vf, minus your Vi squared. And this is what we refer to as the change in the kinetic energy of an object. So the idea is kinetic energy itself is this quantity of 1/2 mv squared. And since I have a Vf squared minus a Vi squared, this is our change. That's where the delta is coming from. So this is causing my delta, and what we've got is a brand new quantity called the kinetic energy. So what I'm trying to show is the work I did, this force times displacement, this work actually caused a change in kinetic energy of the ball. Originally we had 0 velocity, but then after I've done this force, one of the things that you saw is the ball here was moving with some final velocity. And so it went from an initial velocity of 0 to a final velocity as it took off. And this is where work can go. It changes the kinetic energy of an object. This has been the Henstitute, and I hope you have a wonderful day.